Good evening. Welcome back to Sleepy Earth Anthologies. If this sanctuary has been worth coming back to, if the science has given your mind somewhere quiet to go at the end of the day, consider subscribing. It takes a moment, it costs nothing, it allows us to keep building this, and tells us that the work is worth continuing. We think it is. We hope you do too. Now, let's go somewhere interesting. Tonight, we're in warm water. Specifically, in a shallow enclosed lagoon on the southern coast of the island of Vieques, Puerto Rico, Puerto Mosquito, at 3 in the morning. The Caribbean air is still, and the water surface is flat enough to mirror the stars. And somewhere beneath that mirror, in every liter of the bay, there are approximately 700,000 single-celled organisms waiting for something to move. Take a slow breath. Let your body settle. We're going somewhere very dark, and then very bright. Puerto Mosquito is not an accident of geography. It is a specific physical configuration that produces one of the highest concentrations of bioluminescent dinoflagellates found anywhere on the planet, and the reason begins with the shape of the bay itself. From above, the lagoon is roughly bowl-shaped, wide, deep interior, connected to the open Caribbean by a single narrow, shallow channel at one end. This geometry creates a hydrodynamic trap. Each incoming tide pushes seawater, carrying dinoflagellates drifting in from the open ocean, through the channel and into the lagoon interior. When the tide turns and the water attempts to flow back out, it encounters the constriction of the same narrow exit. The outgoing current cannot achieve the velocity needed to carry the organisms back through. The channel is wide enough for the tide to enter, but too shallow and restricted for a mass exodus. The dinoflagellates accumulate. The fluid mechanics of this process are governed by the law of continuity. When a fluid moves from a narrow channel into a wide basin, its velocity drops in proportion to the increase in cross-sectional area. The incoming tidal jet, focused and fast through the channel mouth, spreads laterally across the full width of the inner bay and decelerates almost immediately. The kinetic energy of the ocean tide is absorbed by the volume of the interior. The water inside the bay settles into a slow, barely perceptible gyre, a gentle circulation pattern that keeps the organisms suspended in the water column without sweeping them out. The bay's perimeter is bordered entirely by red mangrove, Rhizophora mangle. The arching prop roots create a dense subterranean lattice that stabilizes the sediment, preventing turbidity from interfering with the optical clarity of the water column. But the more significant contribution of the mangrove forest is biochemical. Mangrove leaves fall continuously into the shallow perimeter water. A specialized community of marine fungi and bacteria breaks down the cellulose into bioavailable organic carbon, nitrogen, and B-complex vitamins, in particular, cobalamin. This leaches steadily from the root zone into the lagoon water throughout the year. The open ocean is largely an oligotrophic desert, nutrient-poor, dilute, and chemically sparse. Puerto Mosquito is the opposite. The combination of physical containment and continuous mangrove-derived nutrient input creates a hyper-enriched growing medium, precisely calibrated to the metabolic requirements of Pyrodinium bahamense. The organisms don't need to forage. They don't need to compete. They float in a medium that delivers everything they need for growth, cellular maintenance, and the synthesis of their luminescent apparatus. Pyrodinium bahamense is a dinoflagellate, a single-celled protist belonging to a lineage that has existed in essentially its current form for over 200 million years. It is roughly oval in cross-section, about 40 to 60 micrometers long, encased in a set of interlocking cellulose plates called the theca that give it a faceted, armored appearance. Two flagella, whip-like protein filaments, emerge from grooves in this armor. One wraps around the cell's equator, driving rotation. The other extends outward, propelling the cell forward. The combined motion produces a slow, spinning drift through the water column. During daylight hours, Pyrodinium migrates downward into the nutrient-rich bottom layers of the lagoon, away from damaging ultraviolet radiation at the surface. It photosynthesizes using chloroplasts embedded in its cytoplasm, fixing carbon and rebuilding its chemical reserves for the night ahead. As the sun sets and UV intensity drops, the cells migrate back upward, redistributing across the upper water column, the zone of physical disturbance where their light-producing machinery will be triggered by the movements of larger organisms. This daily vertical migration is driven by changes in light intensity detected by a specialized photoreceptor embedded in the cell, an eye spot, a dense aggregation of carotenoid pigment granules shielded by a reflective layer of lipid droplets capable of distinguishing the direction of incoming light. The eye spot is not an eye in any complex optical sense. It is a directional photon detector, simple and ancient, sufficient to tell the cell whether it is moving toward or away from the light source. By the time 3 in the morning arrives and the bay is at its darkest, the cells are distributed optimally throughout the upper water column, and the bay contains more living light per cubic meter than any other body of water on Earth. The light-producing machinery of Pyrodinium bahamense is contained within specialized organelles called syntions, membrane-bound vesicles distributed throughout the cytoplasm, visible under electron microscopy as dense spherical packages. There are roughly 400 syntions per cell, each one a self-contained chemical system capable of generating a single brief flash of cold light. Inside each syntion sit two primary components, luciferin and luciferase. Luciferin is the light-emitting substrate, a tetrapyrrole molecule derived from chlorophyll, structurally adapted over evolutionary time for its specific photochemical role. In its resting state, it is bound to a carrier protein that holds it inactive, shielding it from the oxygen dissolved in the cytoplasm. This binding protein prevents accidental, metabolically wasteful oxidation. The luciferin is stored, not available, a chemical charged but latent. Luciferase is the enzyme catalyst. In resting conditions, the internal pH of the syntion is held at approximately 8, slightly alkaline. At this pH, luciferase adopts a conformation that prevents it from accessing luciferin. The active site is closed. The enzyme is dormant. The trigger that changes this is mechanical disturbance of the surrounding water. When fluid shear stress acts on the cell membrane from a wave, a swimming organism, a paddle moving through the bay, It deforms the outer membrane and generates a membrane potential change that propagates inward to the syntion. Voltage-gated proton channels embedded in the syntion membrane open. Hydrogen ions flood inward from the surrounding cytoplasm, dropping the internal pH from 8 to approximately 6.3. This pH drop protonates specific amino acid residues on the luciferase surface, triggering a conformational change. The active site shifts geometry, opening and orienting itself to receive luciferin. Simultaneously, the acidic environment destabilizes the carrier protein, releasing luciferin from its bound state. The enzyme and substrate find each other within the syntion's enclosed volume. Luciferase catalyzes the oxidation of luciferin by dissolved oxygen. The reaction proceeds through a highly unstable intermediate, a dioxetanone ring structure, which decomposes almost immediately, releasing the stored chemical energy. In most energy-releasing reactions, this energy dissipates as heat, the kinetic motion of molecules. In this reaction, the energy is released as a single photon of light instead, peaking at 470 nanometers, blue-green. The efficiency of this conversion is close to 100%. Heat production is negligible. The cell generates light without warming the water by a measurable degree. This is why bioluminescence is called cold light, not because it looks cold, but because the physics of the reaction bypasses thermal dissipation entirely. The entire sequence, from mechanical trigger to photon emission, takes approximately 50 milliseconds. The flash decays over the following 100 milliseconds and is completely extinguished within a fraction of a second of the triggering event. The extinction is not passive. The moment the flash completes, molecular proton pumps in the syntion membrane activate, forcing hydrogen ions back out of the vesicle into the cytoplasm. The internal pH climbs smoothly from 6.3 back to 8. As it does, luciferase loses its protonated state, its active site closes, and the enzyme returns to its inactive conformation. The carrier protein rebinds any remaining luciferin. The syntion returns to its dark, ready state in milliseconds. This rapid reset is not incidental. It is a functional requirement of the system. If each triggered cell remained luminescent after firing, the bay would accumulate a slowly fading background glow that would saturate the visual field of any observer. The high contrast flashing that makes each disturbance so visually precise, a sharp sapphire ribbon tracing the exact path of a fish, a paddle, a breaking wave, depends entirely on the darkness returning between events. The bay maintains its optical fidelity by extinguishing each flash before the next one fires. The threshold shear stress required to trigger the cascade is approximately 1 to 10 dynes per square centimeter. Below this threshold, the cell remains dark, conserving its chemical reserves against trivial background turbulence. Above the threshold, any significant mechanical disturbance, the voltage-gated channels open and the flash fires. The system is a binary mechanical switch with a carefully tuned activation energy. The bioluminescent flash is not an accident or a waste product. It is a defense mechanism, and its evolutionary logic has been refined across hundreds of millions of years of predation pressure. In the trophic structure of the bay, small zooplankton, copepods primarily, graze on dinoflagellates. A copepod swimming through the water column creates exactly the kind of localized fluid shear needed to trigger the cells it approaches. The result, as the copepod moves to feed, it lights itself up, not directly. The copepod has no bioluminescence of its own, but the flash of the cells around it traces its position precisely in the dark water. To a larger fish, a tarpon, a snapper, hunting in the dark mangrove channels, this flash is a targeting signal. The Atlantic tarpon, Megalops atlanticus, carries a retina that is dense with rod cells tuned to peak sensitivity in exactly the 470 to 490 nanometer range. The precise emission wavelength of Pyrodinium bahamense. This is not coincidence. The spectral overlap represents millions of years of co-evolutionary calibration between predator visual systems and bioluminescent prey. The 470 nanometer wavelength also happens to be the band that experiences the lowest scattering and absorption in shallow coastal seawater. It travels further and arrives brighter at the tarpon's retina than any other color would. When the copepod triggers a flash, the tarpon detects it from several meters away, closes on the position with a sweep of its caudal fin, and consumes the copepod. The dinoflagellate cell that fired the signal may itself be consumed in the same strike, but the individual cell is not the unit of selection here. The population is. The flash that eliminates one grazing copepod protects hundreds of thousands of genetically identical neighboring cells from the same predator. The sacrifice is mathematically favorable at the population level, even though no individual cell is making a calculation. This is the bioluminescent burglar alarm. The cell that is about to be eaten activates the security system that eliminates its attacker. The predator of the predator is recruited by the prey. When a wave moves through Puerto Mosquito, the shear field it generates extends through the entire upper water column simultaneously. Millions of cells along the wave's path receive the mechanical signal at the same moment. The result is a coherent sheet of bioluminescence that traces the wave's geometry exactly, a moving line of blue-green light that builds, crests, and extinguishes as the wave passes. A kayak paddle entering the water at 3 in the morning leaves a wake of absolute precision. Each displaced water molecule that exceeds the shear threshold triggers the cells immediately surrounding it, and the luminescent trail maps the paddle's path through the water with an accuracy that no instrument could improve on. The water draws the outline of every movement made through it in cold fire. The light itself, 470 nanometers blue-green, is the same wavelength emitted by bioluminescent organisms across the deep ocean, from dinoflagellates to anglerfish to the photophores of the lanternfish. The convergence on this specific wavelength across independently evolved lineages is a consequence of ocean physics. Seawater absorbs red and infrared light within the first few meters of depth. It scatters UV and violet. The window of minimum absorption, where photons travel furthest before being scattered or absorbed, is centered at approximately 470 nanometers. Evolution, across hundreds of independent lineages, found the same answer. Emit at the frequency the ocean transmits best. The bay in the early hours of the morning is running a physics demonstration that has been running continuously for longer than vertebrates have had eyes to see it. As the first grey of pre-dawn begins to lighten the eastern horizon, Pyrodinium bahamense begins its daily downward migration. UV radiation increases before visible light, and the cell's photoreceptive eye spots detect the shift. The flagella reverse their orientation. The cells sink slowly out of the surface layer, descending into the cooler, darker depths where the sediment-derived nutrients are highest and UV exposure is negligible. Through the day, in the dark of the lower water column, the cells photosynthesize using the diffuse light that penetrates from above, rebuilding their luciferin reserves. The tetrapyrrole substrate is metabolically expensive to synthesize and must be replenished after each night's firing events. The syntion membranes are resupplied. The carrier proteins are recharged with bound luciferin. The luciferase enzymes are reset and tested through the cell's quality control machinery. By late afternoon, the UV index begins to drop. The cells begin their ascent. By dusk, they are back in the upper water column, distributed evenly, chemical systems fully loaded, proton channels closed, waiting in alkaline darkness. This cycle has been repeating in this bay, and in bays like it around the world, for over 200 million years. The geomorphology that traps the organisms shifts over geological time as coastlines change. But the chemistry inside each cell, the voltage-gated channels, the conformational mechanics of luciferase, the dioxetinone ring intermediate, these have remained essentially unchanged since before the first dinosaur walked the earth. The bay is at its darkest hour. The surface is flat and cold-looking under starlight, though the water temperature at the surface hasn't dropped below 28 degrees. Below the mirror, 700,000 cells per liter, loaded, waiting. Suspended in the slow gyre of the interior, their scintillons at pH 8, luciferase dormant, luciferin bound, proton channels closed. Nothing is happening. The system is at rest. When something moves through the water, a fish, a current, a breath of wind strong enough to disturb the surface, the cells will fire, and for 50 milliseconds the water will glow, and then it will be dark again. The flash will leave no residue. The bay will return to dark peace as it was before. The chemistry doesn't accumulate. It fires, resets, and waits. The dark is not the absence of the system, it is the system, resting between events, storing potential, indifferent to how much time passes. Your biology knows how to do this. It has been doing it every night since before you were aware of it. The bay is dark. The cells are loaded. The gentle lap of the bay continues, holding the last shimmer of luminescence upon the water. Slowly, the glow slips away, leaving only the soft breath of the sea and the quiet embrace of the night that continues to hold you. Good night.